Alright, so let's do one more example. Let's find the derivative with respect to t of the following. Y equals 2 over t. Well, first of all, let's consider y equals f of t. We're going to be taking the derivative here with respect to t instead of with respect to x. So this is one of the instances in which we could say, or since we're taking the derivative of y with respect to t, we'll use the notation dy dt. So we're taking the limit as delta t goes to 0, and the definition of the derivative still remains almost unchanged. Instead of x's now we just have t's. So it's going to be f of t plus delta t minus f of t divided by delta t. Now, I guess now it's as good a time as ever for me to introduce another notation. So the delta x's and the delta t's may get convoluted, and it may be difficult to keep track of them when you have a difficult function. And for that reason, sometimes you see this definition of the derivative also expressed in terms of the variable h. And what typically is done is a simple substitution. The substitution that we do is we say delta x or delta t, is equal to h, and we define the derivative f prime of x to be equal to the limit as h goes to 0 of f of x plus h minus f of x divided by h. This makes bookkeeping a lot more simpler. So for this particular problem, where we have y equals 2 over t, I'm going to do this. I'm going to use the substitution. So I'm going to say let delta t equal to h. This will allow me now to take the derivative with respect to h in terms of h instead of t's. So what do we have here? We have f of t plus delta t. So what we're going to have is we're going to have and this is 2 over t, so let me just rewrite this is y equals 2 over t. So what we're really doing is we're taking the limit as h goes to 0. Remember, we're doing the substitution of 2 over, now we have the t here. Well, for t I'm plugging in t plus delta t, but as we just said, I'm going to be plugging in x plus h. So it's going to be 2 over x plus h minus f of t. Well, f of t is just not x but t, t plus h, minus f of t, which is going to be minus 2 over t, all divided by h. So this is what f prime of t is going to be. So let's continue with the work. So we have now a complex fraction. So we're taking the limit as h goes to 0 of 2 over t plus h minus 2 over t, all divided by h. Again, my recommendation: work with the numerator first, and then work with the denominator. For you to combine fractions, if you remember from college algebra, the denominators must be equal. So you have to make them the same. Well, how can you make this denominator be equal? Well, you could multiply one another to find the common denominator, which means that this side is missing a t plus h. So you can multiply both sides, the top and the bottom, by t plus h. And on the left side, you can multiply that by t, because that's what's missing to make the denominators equal. Okay, so in the top you're gonna have 2t on this side, on the left side, and on the right side you're gonna have minus 2t minus 2h. I'll just keep it as minus 2t plus h for now. In the denominator, for both of them now, you're just going to have t times t plus h. Okay, so this may make your life much easier when dealing with a problem like this. So now, instead of having two fractions, we consolidated this into just one fraction in the top. So minus 2t plus h divided by t times t plus h divided by h. Now, keep in mind, you have we have here a complex fraction. So it's, if you remember from, again, college algebra or even pre-calc, we can use the keep, change, flip method to solve this, or to simplify this. So this is limit as h goes to 0 of 2t minus 2t plus h divided by t times t plus h. And this is really being divided by h. Instead of dividing by h, we're going to multiply by 1 over h. So this is the limit as h goes to 0 of 2t minus 2t plus h divided by t times t plus h. And instead of dividing, we're going to multiply by 1 over h. So what are we going to get? We're going to get the following. We're going to have limit as h goes to 0 of 2t minus 2 times t plus h divided by t times t plus h times h. So now we're only dealing with one fraction. And now you could, FOIL a little bit and then factor. So it's just limit as h goes to 0 of 2t minus 2t minus 2h. On the top, in the denominator, we have, first of all, is h times t squared plus th. And here is what I would say is probably the trickiest part. We have to evaluate the limit as h goes to 0. But before that, we should really try to find a common factor of the top and bottom. So let's see what this becomes. So this is going to cancel out. So we're going to have limit as h goes to 0. In the top, we just have a negative 2h divided by h times t squared plus t times h. Well, if h is not equal to 0, then we could cancel, so we could cancel the h's, and we're left with limit as h goes to 0 of minus 2 in the top, and in the denominator we have t squared plus t times h, and my plus and my h and my t's are looking almost the same. But now notice that the denominator is not equal to 0 when h is 0, because when you plug in 0 here, this piece cancels out, but you still are left with a t squared. And this means that we can actually use the substitution method, because we do not get undefined when we plug in the 0 there. So if we take the limit and we plug in for h, this is t squared plus t times 0. What we have is that this is equal to minus 2 over t squared. So we have found the derivative of f. So f prime of t is equal to negative 2 over t squared. That is the derivative of f of t equals 2 over t is f prime t equals minus 2 over t squared. So that is what the derivative of 2 over t equals, is negative 2 divided by t squared. You will definitely see problems like this in the future, of rational functions like this one. Notice this is a legit function. This is a rational function. Rational function. The domain is all t except t equals 0. Except t equals 0. So it's a perfectly fine function. It's actually, it has the same domain as the original function that we had. So it's pretty good. Now, there is an alternate version of the derivative. And this is useful when evaluating the derivative of a function at a point. And the version that I'm talking about is the following. It is f prime of c is equal to the limit as x goes to c of f of x minus f of c divided by x minus c. So this is what we sometimes you see referred to as the alternate form. Of the derivative. Okay. This allows you to actually find the limit of one-sided limits, because you could find the limit from the left and the right of this. So note, you can you can basically use the fact that we can take left and right set of limits for this to find derivatives from the left and from the right. So we can use this form to find left and right sided derivatives. I swear my handwriting is not as bad in the classroom. Hopefully someday you take another class with me and you will verify that. But this laptop has gotten very clunky these past couple of months. In any case, let's do a very important example. Maybe two important examples. And then I'll give you a theorem, and then that will be it for this lecture. This part. So first of all, graphs with sharp turns. So consider the following. Consider the function f of x equals the absolute value of x minus 2. If you remember from pre-calc, the minus 2 there implies that you're doing a horizontal shift of the absolute value graph, and the vertex is moved towards the point 2, 0. Okay? If you were to take the derivative of this particular function at 0, and my whiteboard just crashed once more, so let me reopen it. Alright, let's go back. Alright, so if you were to take the derivative of this, you may have difficulties actually figuring out what you have to do to actually find it. Because the absolute value function is a pretty interesting function, to say the least, to try to differentiate. However, we can definitely see or say something about it. So first of all, notice the absolute value of x minus 2 is continuous. It's a continuous function, so you could draw it without lifting the pen. Also notice the following. When you take the limit from the left and the limit from the right, as you go to the point 2, you may be surprised by what you get. So the limit as x goes to 2 from the left side, let's do the left side first, from the left side of this particular function is going to be equal to the following. It's going to be the limit as x goes to 2 from the left side of the absolute value of x minus 2 minus 0 divided by x minus 2. Why minus 0? Because f of 2 here is 0. Remember, this is the point, this point right here is a point 2 comma 0, so this is 2 0. So f of 2 is just 0. And f of x is just the function. This is f of x. So it's really just the absolute value of x minus 2 minus 0 on the top, and then x minus 2 in the bottom. If you notice, as you take the negative values and values less than 2, what's happening? Well, if you take 1 for example, then in the top you could disregard the 0. In the top you're gonna have something like 1 minus 2 in absolute value, and in the denominator you're gonna have 1 minus 2, right? So it's gonna be 1 minus 2 is minus 1, but in absolute value that's just 1, and in the bottom you're gonna have minus 1, right? So this is scrap work on this top side. If you pick another number, like let's say 0. Not 0.5, 1.5, so you're getting closer to the 2 from the left side. If you pick 1.5, then you're gonna have 1.5 minus 2, and in the top you're gonna get negative 0.5. That is the same thing as 0.5, but in the bottom you're gonna have negative 0.5. And again, when you do this, you again get 1 over minus 1. So we can see that no matter how close you get to this to the number 2, we're always going to get negative 1. 1 over minus 1 is the same thing as negative 1. That's if we go from the left side. If we go from the right side now to 2, we have a similar situation, or at least a similar setup. So we're taking the limit as x goes to 2 from the right side now of x minus 2 minus 0 over x minus 2. But this now is going to be equal to 1, and for the same reasoning, we are picking now values bigger than 2 because we're going from the right. But now 3 minus 2 is 1, 3 minus 2 is 1, so you get 1. If you try another value closer to 2, like 2.5, well, 2.5 minus 2, and then 2.5 minus 2 in absolute value, this is going to be again 0.5 over 0.5. So that's again is going to be equal to 1. If you pick even a closer value like 2.99 minus 2, no, 2.99, 2.001 minus 2 divided by 2.001 minus 2, that's also going to give you 1. Because these are positive numbers in the top, this is bigger than that, so it's going to be positive. And then when you divide by itself, it's just going to give you 1. So we get 1. But notice that here we have a 1. This limit is 1. This limit is minus 1. And since the limit as x goes to 2 from the left of x minus 2 is not equal to the limit as x approaches 2 from the right of x minus 2, if you remember from the definition of a limit, the limit doesn't exist. So this means the limit does not exist at x equals 2. But furthermore, This means that f of x equals absolute value of x minus 2 is not differentiable. It's not differentiable. If you go back to the definition of differentiable, of what it means to have a derivative, it means that the limit exists for all x's. So we have found an x for which the limit doesn't exist in the open interval. The open interval here, it's the whole x-axis, the whole number line, the real numbers. So because we found one point in the open interval where the derivative doesn't exist, then the function as a whole is not differentiable. So there's a way of actually making this function actually be differentiable if you define it piecewise. So there's a way to define it piecewise to make it differentiable. You could define f of x to be I'll have to think about it, but if this was just the regular, I believe it's just x minus 2 actually. It should be x minus 2, and you could say x greater than or equal to 0. And then minus x, I want to say plus 2. I gotta check that. Don't take my word for that. If x is less than 2. It's supposed to be a 2 here. I have to check that. Yeah, I have to check that, but in any case, you should get something like this, and then you could take this derivative piecewise. It is possible, but for the absolute value, what I want to let you know right now is that if somebody comes to you in the train and they give you a function like f of x equals 3 times the absolute value of 3 minus x minus 3 plus 5, let's say, and they told you to find f prime of x, you tell them, f prime of x is not differentiable, or f is not differentiable, so f prime of x does not exist. Come on, erase. You say f prime of x does not exist. Right. Finally, let me just tell you about a little theorem. This theorem means that differentiability implies continuity. And it says the following. It says that if f is differentiable at x equals c, then f is continuous at x equals c. This is a very big statement. It's a very important theorem, because if you know that you have a function and you're told that this function is differentiable for all x's, then you know that that function is continuous at every single point. The converse of this is not true. Okay, so note this does not mean that if f is continuous, then f is differentiable. A lot of people make this mistake. They assume that because a function is continuous, it is differentiable, and that's not the case. This function is continuous, the absolute value is continuous, but it is not differentiable. Okay? There are other functions like it, like the absolute value, that are continuous at all all x values, but they're not differentiable. I'll leave you with an example. an exercise that you may want to try. I want you to show that this is not differentiable. It certainly continues at every single point in its domain, because that's just the cubic root of x. So you could plug in negative numbers there, positive numbers, and you'll get a result. But the derivative of this is actually not differentiable. Well, the derivative. This is not a differentiable function. The derivative doesn't exist. You can explain why by simply taking the limit. Right? That is it for this lecture. Thank you for your time.